Hello and thank you for watching my videos. My name is Astrid Krasniqi. I'm CCNA and CCNP certified instructor. This video we are covering CCNA semester 4, Connecting Networks. This is chapter 4, Frame Relay. Chapter 4 is divided in 3 sections. We have section 4.1, Introduction to Frame Relay. Then we move on to section 4.2, Configuring Frame Relay. And then section 4.3, Troubleshooting Connectivity. Section 4.1, Introduction to Frame Relay. Upon completion of this section, you should be able to describe the fundamentals concept of frame relay technology, including operation, implementation requirements, maps, and local management interface, or LMI for short, operations. Introduction to frame relay. Lease lines, disadvantages. So here, for example, for the lease line disadvantages, because customer will pay for lease line with a fixed capacity. Wide area network traffic is often variable and leave some of the capacity unused. So if we want a frame relay, what do we want is a private network. So with private network, we can buy lease line. We can lease line from Chicago headquarters to Toronto, from Toronto to Mexico City. But the problem here with the lease line is that you have to pay for the fixed capacity in whatever they sell you in increments of 64 kilobits per second or whatever it is, but you can't choose. You can't say, okay, well, I want this much capacity. The second problem with lease line is that each endpoint needs a separate physical interface on the router, which increases the equipment cost. So each router will have a physical interface for each lease line. For example, this headquarter router is going to need at least 4 physical interfaces to connect all these branches together. And then any changes to the lease line generally requires a site visit by the carrier personnel. So for example, if we want to buy a lease line with a new branch office that we have here, first we have to think of 2 things. We have to add another port on our router, and as well as we have to arrange it with the carrier to come and visit our site to actually enable that connection to the new lease line. Unlike lease line, a frame relay requires only a single access circuit to the frame relay provider to communicate with other sites. Dedicated lines provide in increments of 64 kilobits per second, and frame relay customers can define that virtual circuits needs an increment as small as 4 kilobits per second. So if you buy in a dedicated line, you have to pay in increments of 64 kilobits per second. In a frame relay, we can define it, we can be as small as 4 kilobits per second. So we have one link towards the carrier, and then we can create a virtual circuit anywhere we want. So for example, if we want to create another virtual circuit from Mexico City to Dallas, we don't need to get the carrier to come to visit our site. All we have to ask them is to come to enable that new virtual circuit. In the frame relay, the end of each connection has a number to identify, and this number is called a data link connection identifier, or DLC for short. Any station can connect with any other simply by stating the address of the station and DLC number of the line it must use. So virtual circuits. The connection through the frame relay network is between the 2 DTEs is called a virtual circuit. So we have a connection between 2 DTEs. This DTE connects to the DCE, that's a frame relay switch, or the ISP. But that's a virtual connection here we have between the 2 DTEs. So as far as they're concerned, it's like a point-to-point connection from this DTE to this DTE. We don't really worry about what's happening in the cloud. There are 2 ways to establish these virtual circuits. First, it's a switched virtual circuit, which this establishes dynamically by sending a signal message to the network. So this is established dynamically. So it's like similar to the phone call. If you need to send the data, you have to ring the other side, and once the other side answers, you have a connection, then you can start transferring the data. The other one is permanent virtual circuit, or PVC. The permanent virtual circuit is like a broadband. It's always on. It's either idle, you're not sending data, or you are sending data transfer. Virtual circuits are identified by DLCs. So frame relay DLCs have local significance only, which means that values are not unique in the frame relay wide area network. DLCs from 0 to 15 and 1008 to 1023 are reserved. From 16 to 1007 are okay to be used. Multiple virtual circuits, frame relay is statically multiplexed, meaning that it transmits only one frame at a time. But many logical connection can coexist on a single physical line. Keep in mind that dulces have locally significance only and may be different at each end. So for example, dulce 102, it takes you from this area to this side here. Dulce 103 will take you from here to this side. So depending on what is it in front, because a dulce is like a MAC address. So whatever you put in the front, that's going to take you to that destination. Frame relay encapsulation. First, frame relay accepts the packet from the network layer, such as IPv4. Then it wraps it with an address field that contains a dulce and a checksum. Flag fields are added to indicate the beginning and the end of the frame. So frame relay header, the address field specifically contains the following. We have the dulce. This is a 10-bit, is one of the most important fields in the frame relay header. This value represents the virtual connection between the DTE device and the switch. Then we have the CR bit that is not currently defined. EA, extended address. If the value of the EA field is 1, the current byte is determined to be the last dulce octet. Then we have a congestion control, consists of 3 frame relay congestion notification bits. These 3 bits are specifically referred to a forward explicit congestion notification, backward explicit congestion notification, and discard eligible. Frame relay does not notify the source when the frame is discarded. Error control is left to the upper layer of the OSI model. So for example, if there's a congestion, you can mark some of the frames with a discard eligible. So in case there's a congestion, these frames are going to be congested. Forward explicit congestion is as you are going to the destination. So as you send into destination, there's a forward congestion, and the backward explicit congestion is going to notify that as the packet coming back, there's been a congestion. Frame relay topologies. Every network or network segment can be viewed as being one of 3 topologies type in the frame relay. We have star, full mesh, or partial mesh. Star is when you have for example, headquarters connecting with the branch offices. So another name for the star type of network topology is called hub and spoke. Hub being the Chicago here, and the spokes are other cities. Then we have a full mesh topology where you connect every spoke to every other spoke. So for example, there's no hub and spoke. The problem with the hub and spoke is that if the Chicago fails, nobody can communicate with each other. So full mesh is like, okay, well, there's no any hubs here. Everybody will be able to communicate with each other, and it's no problem if one of them fails. We can still have a communication. The last type of this is going to be most expensive, yeah. And the last type is partial mesh. Partial mesh, when you don't want to pay too much for everybody to connect to everybody else, we just connect in like maybe more important branches with each other. So frame relay address mapping. So before a Cisco router is able to transmit data over frame relay, it needs to know what local dulce map to layer 3 address. It's like we need to map layer 3 in the LAN, yeah, layer 3 address, IP address to MAC address. Well, same, we need to map the dulce number, which is layer 2, to an IP address. The address to dulce mapping can be accomplished either by statically mapping it or dynamically. We can static define it, or we can use something called inverse ARP to dynamically map it. So for example, dulce 102 takes it to router 2, dulce 103 takes to router 3, and then these are locally significant. They could be the same dulce's number coming back, or they could be different. So for example, 201 and 301. You can see it on the screen. Inverse ARP. A primary tool of frame relay is inverse address resolution protocol, or inverse ARP, where ARP translates layer 3 IP addresses into layer 2 MAC addresses. Inverse ARP does the opposite. The corresponding layer 3 IPv4 address must be available before virtual circuit can be used. Dynamic mapping. Dynamic address mapping relies on inverse ARP to resolve a next hop address layer IPv4 address to local dulce value. The frame relay router sends out inverse ARP request on its PVCs to discover the protocol address of the remote device connection to the frame relay network. The router uses the response to populate an address of the DLCI mapping table on the frame relay router or access server. On a Cisco router, inverse ARP is enabled by default. For all other protocols, enable on the physical interface. Static frame relay mapping. The user can choose to override dynamic inverse ARP mapping by supplying a manual static map for the next hop protocol address to local DLCI. A static map works similarly to dynamic inverse ARP by associating a specific next hop protocol address to local frame relay DLCI. So for example, when we configure it, we have to go to the interface, give an IP address, and change the encapsulation from default, which is HDLC, to frame relay. Here we disable dynamic mapping. We are saying no frame relay inverse ARP, and we're going to create a static mapping. To configure static mapping, the map between the next hop protocol address and DLCI address, use this command: frame relay map, and then the protocol is IP 10.1.1.2. We are mapping to the DLCI 102. So that's layer 3 mapped to layer 2, and broadcast, and we're using the protocol Cisco. Use the keyword IETF when connecting to a non-Cisco router. Do not shut down, and then we see the interface should go up. So we are mapping frame relay, we are mapping IP layer 3 interface IP address to a layer 2 DLCI address, and we're using a Cisco protocol to use that for this mapping. A broadcast keyword specifies that broadcast and multicast traffic is allowed over this virtual circuit. This configuration permits the use of the dynamic routing protocol over the virtual circuit. So when we do show frame relay map, we should see that we have what we have. Notice that the interface is up and the destination IPv4 address is 10.1.1.2. The DLCI identifies a logical connection being used to reach the interface of DLCI 102, and the other interfaces are displayed on hexadecimal. And this is, we have a static entry, not the dynamic entry. The link is using Cisco encapsulation as opposed to IETF encapsulation. Local management interface, or LMI for short. Another important concept in frame relay is the local management interface, LMI. Basically, the LMI is a keep alive mechanism that provides status information about frame relay connection between the router, your router, DTE, and the frame relay switch, or DCE. So LMI, it just provides the status between your router and the ISP's switch. Every 10 seconds or so, the end device, your router, polls the network. Either they request a dump sequence response, just making sure that you're still there, or the full channel status information. If the network does not respond with the request information, the user device may consider the connection to be down. When the network responds with a full status response, it includes the status information about the DLCIs that are allocated to that line. The end device can use this information to determine whether the logical connection are able to pass data. So when we do show frame relay command, what do we see? The output shows the LMI type used by frame relay interface and a counter for LMI status exchange sequence, including the errors. So we can see that we sent the status inquiries 368 and we have received 369. Last full status requested was 4 seconds ago and we got it 4 seconds ago. It is easy to confuse the LMI and encapsulation. The LMI is a definition of the message used between the DTE, router 1, and the DCE, the frame relay switch owned by the service provider. Encapsulation defines a header used by the DTE to communicate information to the DTE at the other end of virtual circuit. So for all other information here, this is about errors, so they should all remain to 0. So LMI messages are exchanged between the DTE and DCE using these reserved DLCIs. So for example, when we do show frame relay, show interface S000, there are several LMI types, each of which is incompatible with others. The LMI type configured on the router must match the type used by the service provider switch. 3 types of LMIs are supported by Cisco routers: Cisco, which is the original LMI extension; ANSI, corresponding to the ANSI standard; or Q933A, which is corresponding to the ITU standard Q933A Annex A. So local management interface, starting with the Cisco iOS software release 11.2, the LMI AutoSense feature detects the LMI type supported by the directly connected frame relay switch. Based on the LMI status messages it receives from the frame relay switch, the router automatically configures its interface with the supported LMI. If it is necessary to set the LMI type, use the frame relay LMI type and then whatever LMI you are using. Configure the LMI type disables the AutoSense. So for example, interface serial 000, and we're choosing what LMI we are using. The default is Cisco. The LMI is between your Cisco router and a service provider. That's it. It is not from you to the device, to the end device. This LMI is only the status information between you and the service provider. In case where the frame relay switch uses non-default timeout settings, the keep alive interval must also be configured on the frame relay interface to prevent status exchange messages to timeout. The LMI status exchange messages determine the status of the PVC connection. It is important to consult the frame relay service provider for information on how to modify the keep alive settings. The default keep alive settings is 10 seconds on the Cisco serial interfaces, but you have to change it if service provider uses something else. You can change the keep alive interval with the keep alive interface configuration command. Now, the LMI encapsulation that we're using between router 1 and the service provider can be different to the LMI they're using for example, router 2 is using with a service provider. So here maybe we are using Cisco, in here they are using LMI ANSI. It doesn't have to be the same. So using LMI and inverse ARP to map the addresses. So LMI status messages combined with inverse ARP messages allow router to associate network layer and data link layer addresses. Okay, so watch this, what happens here, and it's very interesting. How does the router know about who's their neighbor? So this router 1 has got a Dulce 110 being configured and the IP address 172.18.0.9/30. It's connected to frame relay, and this is connected to another router on router 2 on the other side. And the IP address 172.18.0.10/30, but they have Dulce 100. And remember, the Dulces are locally significant only. So in this example, when router 1 connects to the frame relay network, it sends the LMI status inquiry message to the network. So DTE sends a status inquiry message to the DCE. You say what the wants is the what is the Dulce is connected to. So in this status information. Then the frame relay is going to send it back and it's going to say, okay, the network replies to the LMI status message containing details of every virtual circuit configured on the access link. So DC responds with a status message that includes the Dulces. So it says, okay, well, you have those Dulces. So DTE will learn what are the Dulces. So I got Dulce 101, 102, 103, 110. Great. Those are my Dulces. So now, periodically, the router repeats the status inquiry, but subsequent responses include only status changes. After a set number of these abbreviated responses, the network sends the full status message. If the router needs to map some virtual circuit to network layer address, it sends the inverse ARP message on each virtual circuit. So Dulce 110 is active. I will send an inverse ARP request to learn what is the IP address of this Dulce. So it sends 110, and then 110 Dulce is going to move to the destination. Destination then is going to forward it to router 2. Now router 2 is going to say, okay, well, I just received an inverse ARP request on Dulce, my Dulce 100 from address 172.18.0.9. So let me put that on my frame relay table, or frame relay mapping table. And router 2 is going to respond, says, okay, well, here is the response, and this is my IP address. So inverse ARP response, let's come into the router 1, and router 1 has just learned that 110 Dulce is taken to the IP address 172.18.0.10. So inverse ARP operates similarly to ARP on an Ethernet local network, with the exception that inverse ARP does not broadcast the request. With ARP, the sending device knows the layer 3 IP address and sends a broadcast to learn the destination layer 2 MAC address. With inverse ARP, the router knows the layer 2 address, which is a local DLCI, and sends a request for the destination layer 3 IP address. Advanced frame relay concepts. So here, for example, we have something called access rate and committed information rate. Access rate refers to the port speed. From the customer's point of view, the service provider provides a serial connection or access links to the frame relay network over a lease line. The access rate is the rate at which your access circuit joins a frame relay network. This may be at 56 kilobits per second, T1, which is 1.544 megabits per second, or fractional T1s, a multiple of 56 kilobits per second, or 64 kilobits per second. Access rates are clocked at the frame relay switch. It is not possible to send data at higher than access rate. Committed information rate, CIR, is customers negotiate CIR with the service provider for each permanent virtual circuit. The CIR, is the amount of data that a network receives from the access circuit. The service provider guarantees that the customer can send data at the CIR, or committed information rate. All frames received at or below the CIR are accepted. The CIR specifies the maximum average data rate that the network undertakes to deliver under normal conditions. When subscribing to frame relay service, the local access rate is specified, for example 56 kilobits per second, or T1. Typically, the provider asks the customer to specify the CIR for each DLCI. If the customer sends information faster than committed information rate on a given DLCI, the network marks some of frames with discard eligibility, DE bit. The network does its best to deliver all packets. However, it discards the DE packets first if there is congestion. Aside from any CPE cost, the customer pays for the frame relay cost components as follows. Access rate, the cost of the access line from the DTE to the DCE. Customer to service provider, this line is charged based on the port speed that has been negotiated and installed. PVC, this cost component is based on PVCs. After the PVC is established, the additional cost to increase the CIR is typically small and can be done in small 4 kilobits increments. CIR, customer normally chooses CIR lower than the access rate. Thank you very much for watching this section 4.1, Introduction to Frame Relay. Please have a look at my other videos and don't forget to subscribe. This has been Aslan Krasniqi. Next video 4.2, Configuring Frame Relay. Bye bye.